Hello, everyone, and thank you for joining us today. I am Melissa Russell. I am the marketing director here at Eclipsium, and I'm here to be the moderator for today's presentation, One Bootloader to Load Them All. Just before we get started with our introductions, I did want to let everyone know we are recording the presentation. And after the presentation, we will be sending out an email with links to the slides as well as a link to the recording. If you have any questions during the presentation, please go ahead and enter them into the Q&A panel. We will be taking a look at the questions during the presentation, but we'll also save a little time at the end for some Q&A as well. And at this time, I'd like to go ahead and introduce our speakers. Our first speaker is Paul Azadorian, who is our firmware technology evangelist here at Eclipsium, and he is joined by our Senior Vice President of Strategy, John Lucades. At this point, I'd like to go ahead and turn it over to Paul. Paul, the floor is yours.
Thank you so much, Melissa. It's good to be here. Thanks everyone for joining today. This presentation is based on, as you can read from the opening slide, Mickey and Jesse, as we so lovingly refer to them as, because that's how they introduce themselves for every talk that they give at every conference that I could find. So Mickey and Jesse presented this research at DEF CON 22 this past summer. And
maybe DEF CON 30?
That was DEF CON 30. I said DEF CON because that was the year.
You know, I was with them in DEF CON 22 too, and,
that's right.
And they were there.
There's a long history of John and various other coworkers presenting at various conferences dating back probably to 2017 or prior. So it's wonderful to have you here today, John. I'm very excited to talk about what we turned into attacking and defending secure boot, but we'll also highlight much of the most recent research from Mickey and Jesse centered around how to bypass secure boot.
Yeah, I'm looking forward to it. Thanks for having me, Paul. And I think we're going to have a lot of fun. I always love presenting research with these folks. And as a lot of people know, our team kind of goes way back doing this kind of research. So there's a lot of fun to be had.
Absolutely. So in this presentation, we'll give you a little bit of background about secure boot, what it was intended to be, the design specification at a pretty high level as well. We'll talk about historically secure boot bypasses, and much of that was based on Mickey and Jesse's presentation as well. In fact, at least one of them there, John and I are like, wait, what is that one? Oh, that's interesting. And then we'll talk about at DEF CON 2022, which was DEF CON 30, the secure boot bypasses, plural, that were presented by Mickey and Jesse. Then we'll cover how to protect secure boot against some of these attacks, and then kind of summarize everything at the end. So it's interesting. I really like this quote. It summarizes really in one sentence the intention of secure boot, an important security feature designed to prevent malicious software from loading when your PC starts up. And while there's a lot more happening under the covers, but at a high level, I thought this captured the goal of secure boot to independently and individually verify each component in the boot process.
So if you sort of think back to why would they be into this, there were all of these interesting bootloader attacks going back as far as I can remember. Actually, a lot of things in legacy prior to UEFI were things like master boot record manipulations, and in that process, you get to just add code right into the MBR there and start executing. With UEFI, there was this nice standard to go and create modules, and you have things running from FAT32 file system partitions. And so that's kind of more traditional, and yet still in this sort of obscure part of the boot process. So it's kind of fun.
And it's interesting to look at, John, this was actually your slide, but I really liked it because it draws the lines of what it does and what it doesn't do, which I think is the common misconception I run into, that secure boot was designed for physical protection. In other words, to prevent against the evil made or physical attack. And as it turns out, when I dug into it, Jesse and Mickey are like, no, it's actually to prevent bootkits and software from your operating system having an impact or manipulating software that's involved in the boot process. So it
That's the
detects,
exact distinction that
right?
really is needed to really understand what we're about to talk about, right?
Yeah.
There's
And
a
so
whole
what
different thing for
physical,
protecting against evil made, right?
correct. Yeah. So I mean, essentially, right, it uses PKI to create a chain of trust for software involved in the boot process. It doesn't do prevention or recovery or vulnerability checks, which I think is kind of interesting, whose responsibility it is to identify vulnerabilities in bootloaders and either issue them a certificate or not in the early phase, or revoke them if a vulnerability is found later in the chain. But secure boot is intended to provide that PKI, right? So I also liked where you said you can swap a valid signed bootloader. That's not what
Right.
secure boot does. If it's a valid bootloader in terms of secure boot, then it's valid and it doesn't do any other validation.
Valid, it's valid, right?
Yeah.
So that's the interesting thing, is this is a PKI based security system. So it's going to have every single problem that you expect from a PKI solution. So one of the most common problems is revocation, right? You at some point regret signing something. And when that happens, you have to be able to deal with it. And they've built a system that does deal with it. There is a revocation list. But like every other revocation list I've ever heard of, it's a pain.
Yeah.
And
We'll talk about that.
we're going to get to that. Yeah.
In great detail, actually. So this is a high level of the boot process. Again, we'll actually dig in a little more, but just for setting the foundation, I like to explain to folks, like, the moment you push the power button to the moment you're presented with a login screen or logon screen, however you want to phrase it, there's a lot of things happening inside your computer that get you to that point of actually loading the operating system and presenting the user with a login screen. And this is a very high level overview that once the system receives power, there is firmware that is loaded. I'd say at a high level, firmware's job at this point is to do the very early stages of initialization of all of the hardware. And there's lots of information we could go into there. Once that step is done, it then loads the bootloader for the operating system. And then the bootloader is what loads the actual operating system. In this case, the kernel would be the first phase of the operating system loading. SPI, it's a great question. In this context, is your SPI flash. That is your actual flash chip that typically in PCs is soldered onto the board and represents a storage area for firmware that is critical to both booting the system and other operations.
And this is where, kind of building on what was on the last slide, there's a distinction. You have the SPI flash being trusted. And so you can almost draw a line through half of this slide and sort of say the top half is expected to be okay, it's trusted. And the bottom half is what's being verified. And so it's all about where it came from. On the top half, it's built into the motherboard. On the bottom half, it's something that's removable or replaceable, or some media where you've installed something.
Correct.
And that's where the verification comes in.
Yeah.
So you got these signature checks that are going to be verified as part of the boot process. And this is what's creating what they call the chain of trust. And so you can have a root of trust. In this case, your root of trust, in sort of the simplest implementation, your root of trust is the SPI flash itself. It's that storage on the motherboard. Now you can put a hardware root of trust on top of that, and now your root of trust moves from the SPI flash to something like the silicon in the processor, right? Okay, different ways of starting, but one way or another, you get to this point where you're going to load stuff, and that stuff is a bootloader. And the idea is to sign the bootloader and check the signature using the BIOS, the system firmware, to actually do that signature check. And then the bootloader will do this again when the operating system starts and you actually keep going with this process, the operating system should check drivers, and this is how you root the privilege separation that you expect from an operating system.
One of the common questions that I've been getting, John, since I started here in June of this year at Eclipsium is, well, what about my operating system? When we talk about secure boot, we may talk specifically about Windows or Linux or Mac OS. And yes, all three of the major operating systems collaborate in some fashion to support secure boot as a standard. So Microsoft maintains its own certificate chain of trust. Apple does as well, since Apple, especially with M1 and M2, controls that supply chain and the hardware and the software. They absolutely have their own implementation where they're doing their own validation with their own PKI implementation for their own both hardware and software. Now, Linux, as usual, depends on your hardware and which Linux distribution that you have, and how they have chosen to implement this particular chain of trust. So in Linux, it has been standardized in most Linux distributions, which we end up with like multiple boxes for the bootloader. I don't know if we'll go into that level of detail, but Linux has had to do it slightly differently to maintain that chain of trust. And the last bucket, I guess, well, what about IoT devices? What about my router? And that varies as well. I think, John, from what you and I might have discussed in the past, is that a large vendor that makes routers and switches can, and sometimes does, maintain their own secure boot process. It's an implementation of the standard when they're maintaining their own PKI kind of chain in that point.
I've definitely seen that, and it sort of moves you into that your mileage may vary space, right?
Yes.
Just like Linux, as usual. But one thing that I would point out is, Secure Boot has been around for actually pretty close to 10 years at this point.
Yeah, I think was it 2011?
Somewhere around 2012-ish.
Yeah.
And the UEFI spec actually standardizes this UEFI secure boot that we're talking about. And it is important to recognize that when people say secure boot, they don't always refer to the same thing. Mm-hmm. This specific thing, I tend to clarify it as UEFI secure boot because it's defined in the UEFI specification. There is also the TPM measured boot, which could be a secure boot if you want it to be. But it's really about taking measurements and checking hashes. And then there's stuff like Intel TXT or this dynamic root of trust for measurement, which can cause that to happen at other times than the boot process. So when we're talking about secure boot, we're talking about this UEFI secure boot. And it's important because nearly every system probably has it by default. And that's because for Windows logo, you're going to support this, and you're going to have the specific certificates that Windows expects. Linux will work with that now. And that's where all these distros implemented it, and they all had to do it a certain way. And Linux has a problem that Windows tends not to have, which is you compile your own kernel sometimes. And if that's going to happen.
Yeah, add a module into the kernel.
Exactly.
Which, that threw me through a loop because I'm like, oh, secure boot permeates all the way through to modules loaded in my kernel. And if those modules aren't signed, system will not allow you to load the module.
Exactly. So here is your like standard UEFI slide. And it's funny because Mickey and Jesse have given this presentation, and they've given many other UEFI presentations. And the joke that we like to propagate is that this is the required slide. If you give any presentation that involves UEFI, you have to have this slide.
Yes.
And it's about that old too. But what it's showing is that there are phases, and you can think of the boot process like a state machine, and at some point it changes state. And that's a time, that's an event. And you go through one stage, and then you go through the next stage. And during some of these stages, you run through a whole bunch of different modules. Now, what's interesting is in the case of Secure Boot, most of this diagram is happening in code that's implemented in the SPY flash. So it's trusted. So we're not checking most of this. When are we checking? When you go to the part that it says transient OS bootloader, right? And you're going to start setting up all of this infrastructure for an OS kernel. And then you're going to get this final OS bootloader, and you're going to get this OS final environment at runtime. All of that setup is usually something that you point at. This is the bootloader that's living on the EFI system partition. And that is the thing that needs to be signed.
And I think a good takeaway from that slide and this slide, right, is that up into that boot manager kind of phase, there's software being loaded onto hardware that's initial or running on the hardware that's initializing the hardware. In other words, your memory isn't really fully usable until that code actually runs to make memory usable, which you need
Somebody got to set it
to
up.
load a kernel, right? And I think that's important when we talk about some of the bypasses, that if you get into those earlier phases is why there are bypasses for what you're saying, John, that code
You
just
got
runs.
it.
Yeah.
And you know, like the problem with most security is that it always has a limit, and everyone oversimplifies a lot of security features sometimes by pretending that it'll just cover everything. That's the whole no silver bullet, cliche. But the problem here is it's confusing because there's so many things going on, and it's important to know where the lines were supposed to be. And that's why I'm trying to, really drive home. It's not protecting the SPY flash. That's not the point. And so if you want to go around the whole protection and attack the SPY flash, this isn't the thing that you're dealing with. You're dealing with something like Intel Boot Guard or some other hardware root of trust, different stuff, not this. But now where we get into the fun is that we are dealing with loading a kernel, the initial bootloader. And then we are also dealing with loading kernel modules or device drivers. And so the whole operating system sort of bases its assumptions, its trust, on this chain of trust that is involving a signature check. Now, if you look at Linux, which has to deal with kernel modules and has to deal with you compiling your own kernel, it has a way for you to extend the set of certificates that it's going to check against. And to do that, we go and we sign something called shim with the standard built-in certificate authority. And then it will sign with the distro signature on a particular bootloader like Grub.
Right. So shim is essentially a small little bootloader code that is trusted, signed by Microsoft, third party certificate
They run
authority.
the UEFI CA.
Right. And so shim loads, but then shim has the capability to go, well, I'm going to load Grub because it has a valid signature, and Grub goes, I want to load the kernel and its modules because I have valid signatures for those.
Exactly. And you want to think about the shim as the commonly signed, rooted back to a common certificate authority, the thing that extends that set of certificate authorities with something like a distro certificate authority. And as it sort of moves on, that's where you get into Linux kernel modules and compiling your own kernel. And there is a way for your system to add something that just your system approves for signing, so that you can sign your own kernel or module.
Machine owner key is what, if you want to.
Machine owner keys is the word, yeah. So what we are protecting against with Secure Boot is this idea of replacing or modifying a bootloader, right? And that's where you go back to all those MBR type things. If you can add code there, you can modify code, you can replace the code, you get all sorts of interesting properties because you're running first. And you can mess with the operating system while it's trying to do what it thinks it's doing, right?
Yeah, I mean, that essentially sums it up.
If we kind of look through UEFI, you have all of these services and standard sort of functions that are defined by the UEFI specification. And some of those are the things that tell us which specific bootloader to use, what the order is. There's a whole lot here, but remember, just like you were saying, you know, most of this is designed to configure hardware, to like initialize your system, to get the environment ready for an OS.
And this is all happening in the DXE or driver execution phase in this slide. Is that correct?
The way it's set up, it probably was being set up in the Dixie phase, as it's called, but it persists, and it can be used in later stages. Even some of these protocols are available at runtime. That'll be called the runtime interface.
And so like Dixie itself is 2,500 pages of the UEFI specification, which is why if you're seeing terminology in here that you don't quite recognize, there's a lot in the specification defining.
And we simplified it, let me tell you.
Yeah, exactly. But the point is that it's defining, the specification defines this process in great detail.
This is probably the slide that I think you were kind of getting at here, where you're looking at some of these are runtime services that stick around. Some of them are boot services that are only used for the next stage, right? Some of them are internal services that Dixie will use for itself. The reality is that there's all this extensibility, like literally it's in the name, the Unified Extensible Firmware Interface, UEFI. And that extensible part is this concept of the modules that you can add to and mess around with. And that's great because it standardizes things and lets people actually reuse code. But the weirdness is that it's in this obscure place where running in one stage gets you a certain set of capabilities, running in a different stage that could be completely different. So you have this concept of device drivers, and you actually have this concept of UEFI drivers. Usually when you say a device driver, you're thinking about something in the operating system.
Yeah.
A UEFI driver could be doing the same sort of thing that a driver, in your OS would do, like accessing a RAID controller. But it could also mean this Dixie driver that's really just a module that sets up some stuff. And that could be related to hardware. It usually is. But it could actually be software.
I think of the Dixie phase, as you see that terminology on multiple boxes here, right, as doing the like basic lowest level stuff to initialize the hardware, to make it usable for the next phase, to bring up your RAID controller so that the kernel drivers can then read the RAID controller. So like this pre-initialization phase.
And there's even more of that happened before this, and you can keep going.
Each phase sets up. Right.
Yeah. This is where we have fun with research. But back to this talk. There's been a bunch of these before. Paul, did you want to talk through some of these, or do you want me to?
Yeah, I mean, we can kind of tag team it, right? So golden key is allows anyone to bypass, which allows you to unlock any device that's protected by secure boot. And this is Microsoft accidentally leaked a key, right? If I understood this one correctly.
I don't remember who leaked it, but yeah, there was one key that was like, okay, it'll work on everything. And once you have it, it's like it's going to work everywhere, right? I think this next one is actually more recent. This one was back a ways. I guess it says 2016. So yeah, I remember this being a thing quite a while ago.
But I think that led to Microsoft asking harder questions about how you protect your key when you've given them software to be signed.
That's how it always works, right?
Yeah,
like if you, I mean, I don't take this the wrong way. I'm not really thinking that I don't throw Microsoft under the bus. Like if I did this, it wouldn't be any better. Like you're gonna go through this refinement process, and no matter how much you like overthink it in the beginning and try to like get everything right, that never works. And so you're going to end up with a process that matures over time. And, you're going to get things like, oh yeah, so that thing we were doing for debug in manufacturing or whatever, yeah, that's not cool.
Yeah, it's interesting too. A lot of these vulnerabilities and the one we'll talk about it, that Mickey and Jesse disclosed, some of them, I believe, led to Microsoft publishing like this obscure tech article. It was like, hey, when you submit a software, it now has to have this security feature, right? And so that's the process that John's speaking to, is that what I like is oftentimes our research and other people's research in this area leads to actual change happening.
I think that's the point. I mean, that's why I'm in it anyway.
Right.
There's also this.
Yeah,
go
baton
ahead.
drop was interesting, right?
Much newer.
Because yeah, it's newer. And so when we talked about those different phases, what I got from this was basically if I can affect change in an earlier phase, like before secure boot starts happening, I can like remove the policy and just say like, oh, yeah, secure boot doesn't really need to happen, right? Essentially. You still there, John?
I am. I think I dropped for just a second.
Yeah. I was just saying this bug can basically remove the secure boot policy, right? Because there has to be a policy to exist to say, hey, I want to actually implement secure boot. Well, if you like remove that piece of code, this sounded like it was doing it through memory, right? Like basically invalidating the memory where the policy would live, which means secure boot doesn't get loaded.
You're going to get to some fun bits where this is similar to what Mickey and Jesse did in their exploit. And it reminds me of one of the first secure boot bypasses that we published probably back in 2013 or 14, which was actually to overwrite the secure boot policy. Same idea, but in a UEFI variable. I think they did this in memory here, but it persists in the UEFI variable if they did it wrong and it's accessible but this happened. And over time, that I think it's that refinement of finding these sort of bugs and fixing them that, kind of going back to all the rest of this. Oh, yes, the Kaspersky Rescue Desk.
Yes.
I love this.
They produced this rescue disk as like a recovery tool. And in order to recover a system that has secure boot enabled, their recovery disk has to contain boot software that's signed in the process.
Yep.
But
so it'll work with your secure boot, right? So
but there was a
rescue disk.
There was a way to bypass it to make it load any other kind of bootloader that wasn't signed, essentially.
It's always like the easy way out, right? If you have a thing that's just going to load another thing, but this thing is signed, you just broke the whole point of having secure boot. But hey, it lets you do what you're trying to do. That's cool. We're going to find that keep that one in mind. That's going to come up against pretty soon.
And that's different from Boothole. Boothole was more of a vulnerability inside of Grub 2 that an attacker would exploit in order to bypass the secure boot process.
Exactly. So there's the easy way out, and then there's the hard way, right? Like we actually have to exploit something here.
Yeah, like in this was more of a configuration inside the Grub configuration.
It was loading the configuration file, and that, since it was exposed, can be modified. And that is the thing that is that when they were parsing it, there were some bugs. Yeah.
And they also went on to find more. So some of the confusion I've seen online, right, is that the Linux community and specifically the developers behind Grub went off and found more vulnerabilities, which leads to the certificates being revoked for more different versions of Grub, which means when you take your USB thumb drive and you go boot it on a computer that's configured for secure boot, it goes, I can't boot. And it's because you haven't updated the version of Grub on your thumb drive, as an example.
I mean, you've got two kind of horrible choices, right? You either didn't update the DBX, the revocation list, and it will boot and you're still vulnerable, or you did update it and now it won't boot, right? So like back to the rescue disk concept, it's tricky.
Right. This slide is speaking to our previous slides, but in a slightly different lens, I think. Intel defines those processor rings. Anyone listening, right, that's taken a class in computer science and operating systems has probably, had a slide from your professor that was like the different rings, right? And I think the research community, when we get beyond ring 0, has started to define the deeper level rings, where the hypervisor is at ring 1, SMM, which is the system management mode, processor state which has a lot of interaction with UEFI, is at ring 2, and then your management plane, or management, I should say not plane, it's more of like a system. It's
It's like a chip, little CPU on the chipset.
CPU and RAM on the chipset. They can operate independently of the main system hardware and software, which puts it at ring 3. And you can look at my blog post series where I cover firmware security realizations. I cover secure boot, Intel ME, and SPI flash protections. Is a good kind of follow on to this slide, especially.
Yeah, and it is sort of a reasonable extension to this concept of this ring model, where what was actually defined was, the positive ring 0 through ring 3, and then we're going negative, and meaning that we're more privileged than ring 0, more privileged than the OS kernel. There are things that we can do that even it can't do.
I've read SMM described as you can halt operating system functionality and do stuff outside of the purview of the operating system.
And in fact, that's what it's for. And so that kind of leads you into so that it's used for something like in the positive sense, it has a purpose. But there's also this negative sense of, well, when you're attacking a system, there's things that you can do now that are not normal, right? And they're outside of the space of what people expect.
Yeah, and I look at, it's interesting how I've been lumping everything prior to the kernel as these lower level attacks. It was interesting that they're not necessarily all firmware, right? We talked about bootloaders, we talked about master boot record, which is an older technology, and we talked about kernel drivers. Those are not necessarily firmware based. They have interactions with firmware. But the reason you would go to that pre-kernel phase, right, is stealth, because like I said, SMM mode, right, operates independently of the operating system as an example. Persistence, if you put a new operating system, but you still have code that's outside the purview of the operating system, you still have code running. You can just reinfect new operating systems that are installed. And also when I looked at impact, it was the more privileged you become on the system, the greater the impact you can have. If you want to just take out certain components or complete destruction of the system, you need a much higher level of privilege. And the higher level of privilege that you become, the more damage you can do. If you're at that Intel ME phase, oh boy, look out.
Yep.
Yeah, there is a comment that SMM runs in a separate mode. It's not a specific ring. I think it's what we're saying is it.
Yeah, so there's some technicalities here that we kind of glossed over.
Yes, I agree with your statement, Monty. I agree wholeheartedly.
Yeah, the actual definition of stuff versus, what people have said, which is fair.
Yes, SMM in fact implements all rings. He says hypervisor runs in a separate mode, even if it has all 4 rings. That is technically correct.
That is all correct. Yes. Oh, and it's Monty. Hi, Monty. Very cool to see you here.
Oh, this one's interesting. Interesting too. Gamers that want to implement cheats have to go to these lower levels in order to get the game cheats to work. And I haven't studied this like in depth, John, but based on what I just said in the previous slide, this would make perfect sense if software within the operating system is putting controls and protections in place. The way around those is to get a higher level of privilege on the system and drive deeper.
Yeah, I can't stop enjoying how funny this is for me, because like I spent a long time trying to learn this stuff, and I know a lot of other people who did too. And of all the reasons to go into it, cheating in games is sort of the funniest thing for me. But it is a thing, and it actually, there's truth to this statement here. Like, this is true. I'm always shocked at what people will do just to get cheating to work.
And Mickey and Jesse went into more in-depth explanation in their presentation, which usually it's a year before they publish those videos. But if people are interested, contact us. We've got more information to share on that topic if you're interested.
Absolutely. And as always, in general, for all of this firmware related stuff, that's what we like to do.
That's right.
All right, so on to the actual bypasses that were discussed here. So that's sort of the background, the history into how we got to where we are and why these things matter. And if you think about what actually was presented and like what are the very specific things that are wrong, there are 3 CVs. And here they are. And each of the 3 CVs corresponds to a specific bootloader that is signed. And so it's got that signature that will allow it to boot on any system with the default built-in certificates. Each one of them was sort of, you can sort of see it was for a different reason. It had a purpose of some sort. 2 of them sort of fall into this. I'm sorry, but I find these things funny. And I know a lot of you who are probably listening in may well be deep into firmware, and not everyone necessarily appreciates my sense of humor, but I find it really funny when people sign something like a UEFI shell. It's exactly contrary to the purpose of having signed bootloaders. Like, you're not supposed to be able to just do anything. But hey, it happens, or happened at least twice.
I mean, it's kind of, it's similar to like if I were to sign a kernel and say you could load any module that you wanted, it would completely defeat the purpose of signing that.
Why
kernel,
sign a kernel?
right?
Yeah.
And same
And
thing
in
with
fact,
the
that's what the
UEFI
Linux
shell, right?
was.
It's a piece of code that's
Yeah.
signed that can load other pieces of code and circumvent the process.
Exactly. So you got this signed shell, which is clearly designed for, running whatever. And then you've got this other thing that basically just loads and executes something else without checking a signature. So it's a lot like the Kaspersky rescue disk sort of case. And what we're going to talk through is in the exploitation of this, what Mickey and Jesse put out, and this is available on GitHub, and you can see the whole presentation, you can get their code, you can sort of recreate the whole demo. They created this unsecure boot little app, and let's just go run that, and we'll talk about what it does. But the idea is that this is what gets you to the whole I can run whatever I want. And there's some like little gotchas in terms of, so how do I actually get from code execution to actually running?
So you're taking any of these 3 bootloaders and essentially installing them on the system to be able to run whatever you want.
Exactly. Well, so you swap files. So
swap files, yeah.
The important part here is that UEFI bootloaders are files on a FAT32 partition. That FAT32 partition happens to be called the EFI system partition. And the concept behind all of this is that I'm pointing at a file. We're going to load and execute that file. And what we've added is a signature check on that file. And since these modules are basically PE files, we can basically reuse the Windows signing of an executable concept.
Right.
And that's basically what these are. And so if you get a shell, then you sign it. It turns out that I can drop that file on the ESP of any computer. And as long as we signed it with a CA that everybody recognizes, well, and by the way, there is one, the one that Windows uses. Hey, cool, I guess that's gonna just work. And so now the question is, what do I do with a shell? And if you, I think we're gonna talk a little bit more about it later, but if you think about what a shell does, most people aren't familiar with the UEFI shell specifically, but you probably have used, the DOS command line, or you've used Linux and Bash and that sort of stuff.
I think if you've had like horrendous problems with your system and had to have used a UEFI shell, it was not a good day for you.
Probably. And that sort of a thing, replay it. It looks a lot like DOS. Go play around, CD this, CD that. Right. But it has some direct primitives that are commands, like reading and writing memory, right? And you can sort of poke at specific memory and just do whatever. And as long as you have those commands built into the shell, which they do, hey, cool. This is going to be not that hard.
Right. John, have we seen any bootkits taking advantage of any of the vulnerabilities we've discussed up to this point? My recollection, I mean, just, spoiler alert, John and I have, and many others at Eclipsium, have spent a lot of time talking about what real world attacks are and making lists of them as well. And so specifically, I don't remember one that took advantage of the secure boot, but I could be wrong.
So the ones that I saw earlier last year, I think, were the EFI specific ones, but they were not signed. So they did not try to use this technique to evade. This is actually fairly similar to the same technique that you use with screwed drivers, which we published a long time ago. This is basically signed device drivers. And malware has packaged those signed driver with vulnerability, or maybe you could call it feature abuse if you depending on what you think the driver is supposed to do. But if it allows you access to do the thing that you want to do, you package it along with your payload and your malware, and now you have kernel level access to whatever that thing is. Same idea here, except it's a bootloader instead of a driver.
Right.
So the third one is in some ways the fun one. I mean, the first two are kind of more funny, I guess. This one is fun because it really is the same concept as what happened with the Kaspersky rescue disk. You're going to run this signed thing, and this signed thing is going to go look for this very special file with that very special name. It's going to go load that, and it's going to run that without checking a signature. Okay. So this is also fun, but you're going to start to get into sort of how does exploitation work for something like that. And even for the other one, what makes exploitation work is maybe the best part, and I'm just making sure that I'm not skipping ahead too much. The best part is that what Mickey and Jesse did was find a way to go and basically zero out the handlers for all of these security things. And these security things include the authentication, the signature check. And it also, by the way, includes the TPM. And so when you load a UEFI module, you take the hash and you extend the TPM PCRs with the hash of the thing that's about to be run. The whole premise of the secure boot sort of chain of trust, they call it, is that the thing that's running needs to do that, and you trust it to do that so that it will extend the chain. If it fails to do that, you're in trouble. Well, if we zero out the handlers for these security features, then there are no handlers. And then when there are no handlers, it doesn't do those things. It's really quite simple and involves writing 0 to the right place. So that's pretty kind of awesome.
So the SHD manager, the code you would load in there is to zero out some of those handlers.
That's what Mickey and Jesse did. And that is the unsb project on GitHub. You can go and grab that, and you see what they're doing is just a very simple, like, oh, we get this pointer over here, we get this pointer over here, that'll be 0. And what happens now is that everything works, everything runs the way it's supposed to. It just chooses not to run the actual signature check. It chooses not to run the TPM extension. So what that means is that things like BitLocker are in jeopardy, right? The PCRs are supposed to change when you swap bootloaders. Ha ha ha! Not anymore.
Not anymore, because we told them not
so
to.
like,
yeah.
This is a problem. So this is why all of these vulnerabilities, all 3 of these, so I'm spending a lot of time on this one, but the other 2 are just as bad because they let you do that, whether it's by a command in the shell, or it's by loading, compile some code, let it load and run. That's what you're going to end up doing. And the result will be secure boot's still on, by the way. It's still working. It's just not doing anything.
Given the appearance of working to the end user. If you were to check, it would say secure boot is enabled.
And that's exactly what happens in their demo. So it sort of leads you to this ugly place of, so this is where we live in this ugly world of, I really needed to change my background to that, this is fine dog with
Yes.
the
Everything's
fire.
fine. Everything's
It's
fine.
fine. This is like everything else. It's not
As long as
highly
we don't sign
unusual.
things that have vulnerabilities, everything is fine.
Yeah, exactly. So good luck with that. And the situation of finding more of these things is not terribly unrealistic. In fact, don't be surprised if there's more.
Right.
And this is like many other PKI based things where you sort of see somebody will find something eventually. And so it gets into the fix. So there is a process, there is a feature in this process that allows you to revoke, and it's critical for exactly this sort of thing. But people actually have to do it, which is the interesting part.
Right. And that's where we get into the DBX, which if you have secure boot enabled, DBX is a variable that stores multiple hashes or certificates for software that has been revoked. And I think there was a question in the last webcast, right? Secure boot checks that list first. Like if you manage to have a hash in the DB, which is the allowed list of software to boot, and one in the DBX, which is the revocation list, secure boot will always check the DBX first and go, no, that software is not allowed to run.
Well, or at least it will override with that. So however order it is.
Well, and that's also implementation specific as well. We hope that they got that right in the implementation as well.
Exactly. Yeah. Exactly.
So this leaves systems in a state where this list has to be updated. And I think when we talk about Apple and Microsoft, they are pretty good about updating this list. Apple and Microsoft take care of that for you, correct?
In general, yeah. But only on their devices, right? So if you're Apple, well, Apple is going to control everything very, very tightly.
Right.
And on like a Microsoft Surface device, they know exactly what their firmware is. They can test it. They are very comfortable with deploying that sort of thing. When you're getting into everything everywhere from every manufacturer and every version of it, that gets a little complicated.
So they won't automatically push it out if it's not a Surface. They leave it to the user to go, you have to have some control, because if you are running a bootloader that's vulnerable and you update the DBX, your secure boot is not going to let you boot the system.
So I'd sort of say it more like your mileage may vary, right?
Yeah, it depends.
In many cases, they have done this, at least with this one. In the past, in the last one, they didn't. What's kind of special and fun and interesting, and I think this is the first time I've seen this, is that on Linux, there is an automated process with LVFS now. And they actually included the DBX update. So I actually had this pop up on my system, and it works.
Yeah. So on Linux, in that blog post, I actually dig into, there is a mechanism within your Linux distribution, Ubuntu as an example, right? It's going to vary, but there is a mechanism where the distribution, like Canonical, could push out a DBX. There's actually scripts in there to do that. Now, they haven't done that for the latest revisions of the DBX. So my post shows you how to do it manually. Richard Hughes of the LVFS project, Linux Vendor Firmware Service, in the latest versions of 1.8.5 or above, gives you the facility through LVFS to apply a DBX update to your system. So anonymous attendee is asking for Linux if these fixes are included in the 6.0 kernel. It's a great question. This is independent of the kernel. So this is a process that has to run on your system and update a UEFI variable. Correct? I get that right.
No, you got it. And it's a lot closer to like a BIOS update without actually updating the code of your BIOS. Correct. It's updating data, which is in this case think of it like the root certificate authorities, and that's basically what they are.
Very similar. So I ran this through the command line and gave everyone a screenshot. So what's interesting, you can actually go to the LVFS website and see kind of a history of various DBX updates, and Richard gives them a version number. And so before Mickey and Jesse presented at DEF CON this year, the latest version was 2.11, and that was addressing vulnerabilities in Grub specifically, and maybe others, right? And that was the latest DBX at the time. However, when new vulnerabilities are uncovered, whether it be Grub or other bootloaders, you need to update your DBX. So the latest version is now 2.17. And you can see this is the process you would go through on the command line. There's also a GNOME snap-in for that. And Richard has given us some data on that as well, which I think is really interesting. And again, I didn't include the link, but there is a link where you can go find the page where Richard maintains the DBX update.
Well, and the UEFI forum maintains the DBX
Correct.
update at uefi.org/ something like
Downloads.
revocation file.
It's in my
But if you Google it, it'll be up there. But it's on uefi.org. And that is sort of like the central place for the file. But you need to follow the manual instructions that you posted in your blog in order to use that.
Right.
LVFS automates this, and it's super cool that they finally have this. And more importantly, it's in all the. It's like so many distros have it now, and it's like by
but
default.
Not all the distros have updated. Yeah, not all the distros have updated from 1.7 to 1.
That's true. That's true.
8. So you're going to see this number jump up.
And already you're getting to like 2-something million. That's pretty awesome. And that's new, right? This is something that, the first couple of times that I worked on issues in UEFI space, right? I don't think we got that kind of thing because there was no automated like updater that would just do this.
Right.
Some of the OEMs have their own BIOS updaters and that sort of thing, but this is more of a centralized thing across multiple distributions of Linux. And I'm kind of impressed that there's this many people actually updating their DBX now, which is great.
This is exciting.
Although apparently a lot of them are from India.
Apparently.
So this is a breakdown from geography. And, I kind of expected the US to be up there at the top, and no, actually it's not. So it's kind of cool. And remember that this is specific to Linux. So these are going to be Linux users. They're going to be people who are actually updating. So they're probably on like maybe the newer versions of maybe a fresh install or something like Fedora that they're kind of keeping up with all the time. But still, that ended up being a lot of people. So this is the sort of thing that we're trying to accomplish, if you think about it, changing the ball game so that it's not this unknown area that nobody touches and nobody can see.
Correct. It doesn't come without warning, by the way. I think we've already spoken about the potential pitfalls of updating your DBX. I mean, it could cause problems in general, right? So like do this at your own risk, make a backup of everything, the whole thing. Specifically when Microsoft, so based on Mickey and Jesse's research, Microsoft said, well, we're going to push or make available a DBX update. People started applying that update and it caused some issues. It caused specific errors to occur, as well as BitLocker recovery keys being asked for.
So there's like 3 different incidents here.
Is there 3 different bugs? Okay, I think
at least
I tracked at least 2.
At least, I mean, there might even be others that I'm not remembering right now. But in the Kaspersky case, they actually revoked the Kaspersky bootloader, but then stopped shipping that update because it broke stuff. Right. Actually, at the same time, there were other bugs that like you could sort of go back into the Linux kernel stuff and start looking at. There was another problem with like kdump, where it was putting too much stuff in a UEFI variable and it would brick a certain system that just didn't handle it right. But when your firmware doesn't handle it right and it breaks, this is a big problem, right?
Yes.
So they stopped pushing it. They had the update, but you had to do it manually. And then when we had the boot hole issue. In that balloon, just like you said, where, you know, we found some stuff and then like more people found stuff and oh my gosh, like everything is a mess. Well, that adds a lot of stuff into your revocation list, right? So you start thinking about, how am I going to manage this? And one of the good things that came out of it was better ways of managing the revocation, which,
Right.
you know, Microsoft did implement.
And
So
warnings
now we
too.
got to see that in this latest one. The 3 new ones, when they revoked it, they actually had a little bit more confidence and did push it at least to some systems on Windows. But you can see that even with all of that confidence, it still broke down in certain places, whether it was a BitLocker recovery or didn't take and just failed, you know.
Yeah, and I think one thing that maybe isn't in the spec is, what if you're applying a DBX update and your system is using a bootloader whose hash is in the DBX about to be applied, what should the system do? Should it stop the update? How should it warn the user of that? I believe it was LVFS that was reading some posts online where that was happening to someone, and I was like, no,
That's
like,
very unfortunate.
it's doing what it's supposed to do. You need to make sure you update your bootloader. Now, most
There's some
folks,
face palm there.
yeah, but now
Ooh.
most people will get the updates from their operating system, and your Grub, for example, will come down in an apt update, upgrade process. So that shouldn't be the case. However, if you are running it, like if it applies it, it means when you boot back up, your system's not going to boot.
Right.
Also the case with BitLocker, if you push out this update to, let's say 20,000 Windows systems in your environment, and they all, I mean, I don't think it was every configuration and use case, but let's say
Like certain
10,000 systems are in a BitLocker recovery
But
mode. Like,
1% of a lot of systems is still a lot of,
yeah,
you know,
yeah, give your
it's gonna
help desk
be
a heads
bad.
up, because that's going to be a bad day.
Yeah. So those are things you, and by the way, like that situation is a lot more, there's a lot more capacity for you to deal with it than if it breaks, for example. So like you can package the update around other administrative activities that would prevent the recovery, the BitLocker recovery. You can do other things, but note that there are dragons around here somewhere, and you probably want to do things. And probably top of that list is testing.
Yes. We have 3 minutes left, so if people have a few last questions, we can try and address them as we wrap up. We did mention the machine owner key towards the beginning. UEFI does, I believe this is in the specification, right? Where you can provide a facility where you can have your own key. So like you can maintain your own chain of trust. You can create your own certificates. You can sign your own software. Of course, that means you will have to do that every time a piece of software in the chain changes, or you load a new kernel module. It ends up being a lot of work. It is certainly possible. There are some people that do it as an end user, maintaining it. And again, this is how a big manufacturer of routers and switches, if they want to implement this on their systems or what have you, or their appliances, they could maintain their own system of trust if they control that software. What I don't like doing that in a Linux user is I don't control a software coming down to me, which is like a whole other presentation. But then I have to validate and sign the software that's coming down to me to maintain that system of trust. So
let me put a different spin on that, which just is a different way of looking at it. Everything is correct, but if you think about this as a software supply chain problem, and you think, well, there's different ways I can tackle that problem. One is that I follow what everyone else is doing, and at least I'm not any worse than the next guy. In many ways, this is the bear analogy, right? Like,
right.
Cool, I don't have to outrun the bear. And, to some degree, there's truth to that, unless you happen to be targeted by the bear, and that means something entirely different. But if you are, if you're really very locked down and you have an environment that you control very precisely, you can take over the whole process. And that is this idea of custom mode, which is what they call it in the spec. where you substitute your own root CA. Now you got to run a CA, which, you know, have fun with that. That's also really cool. But now instead of relying on somebody else for this problem, at least you're bringing it under your own control. So if you're ready to take that kind of control, you can. But it is a lot of work. So that's kind of what this custom mode thing is all about. And I do look at it a lot like a supply chain problem, because that's what it is.
Yep,
it's the supply chain of all that software that's running before all that software that you're actually managing.
Right. I think that was the last. Was that the last slide? I don't think we had.
That is the last slide.
Look at that. Wow, we ended exactly at 2 o'clock.
Cool.
We got, of course, we got a question that came in right off the top here, but let's just address this one and then we'll go ahead and wrap it up.
Yeah. What is a
someone
good
said-
solution for open source supply chain attacks? Sorry, Melissa. I didn't
Yeah.
Step on you there. Yeah. That's a pretty good question.
Out of topic. Yeah. So we're talking about like generic open source stuff. So I would sort of break that into two problems, right? And this is my typical answer to all of these things. So I don't have a single silver bullet. I don't believe in them, to be perfectly honest, because you're going to have more of these, and there's going to be a problem. So how are you going to deal with it? You probably need two things. You need a thing that looks for anomalies. Now, those could be vulnerabilities. Those could be some sort of a unauthorized change, if you will, but something that looks for this sort of deviation, this anomaly. But you also need something that looks for tampering. And so you have the concept that a thing was actually intended to be released. It was official, and you're looking for it to do weird things. Or it was not officially released. It was tampered with, and you want to actually find that change. And so I think that's two problems, and there's two different pieces of technology. At Eclipsium, we actually try to do both. We profile these, firmware things, and we try to find deviations. And we also look at sort of measurements of these things and try to find change. I would apply that to the other open source software as well, and look at, we have a specific repository, does what you have match? That's going to catch tampering. But then you also want to have almost like a model or a profile of what that thing is supposed to be doing. And if it deviates from that, yeah, you probably want to look into that.
Yeah, and I think it's different on the software side, in software libraries in popular frameworks like NPM and Python and what have you, right? There's solutions out there for that that I can't recall off the top of my head. There are open source ones as well that you could find. Like I separate that into, like, I'm developing or packaging software, right? But I'm also like running software on servers and endpoints, and I need to validate that as well. Tends to be two separate. One's the developer problem, and one is the IT infrastructure kind of problem.
Right. But both of them have to solve the two cases that I was talking about.
Absolutely. Yes.
Yeah.
Correct. Awesome.
Well,
Thanks
gentlemen,
everyone for joining us.
I think we have concluded this. I did just want to thank everyone again for taking the time out of their day to join us. And like I said, we did record the presentation and we'll have the slides available, and they'll be made available here within the next 2 days. Thank you again, John. Thank you, Paul. Appreciate you joining us.
Thanks, everyone.
Thank you.